Okay, awesome. We'll get started. My name is Abby Feeder. I am the team lead for the Aerostructures team for ARES this year. We are known as Project Prometheus. The rest of the team's going to go through and quickly introduce themselves.
Hi, I'm Brendan Coy. I'm the System Integration Engineer, and I'm also the Financial Manager.
Hi, I'm Cooper Cromley. I'm the Surface Integration Engineer, and I'm also the Procurement Manager.
Hello, I'm Matthew Hutchison. I'm the Body Structures Engineer and working as the Test Manager.
I am Danny Ewell. I'm the Structural Connections Engineer and the Risk Manager.
Hi guys, I'm Cody Monteith. I'm the Internal Structures Engineer and the Safety Manager as well.
Hello guys, I'm Noah Williams. I'm the Support Engineer.
So this is just kind of what we're going to walk through today in terms of the flow of how we're going to break down the system. This is kind of how our subsystem fits into the overall goals of the vehicle. So right now the ARES mission is to develop a pressure-fed liquid rocket engine, and this first generation vehicle has a goal of launching to 45,000 feet. As you can see in this kind of tree diagram over here, there's a lot of different subsystems that go into it, and we're kind of highlighted here in red. So we are working to have on basically support all of the other subsystems that are making this rocket fly. And obviously the main goal of this is to be able to recover the vehicle with the hardware intact. This is an image of our current vehicle concept. It has some placeholder tanks and stuff in it, but we're going to go more in detail about the specific nature of the structure itself. This is a little bit of our work breakdown structure. This top image up here is kind of the first level of flow downs. As you can see, there's about 6 or 7 different areas of the design that we have decided to focus on and break down further. Those include the body tubes, the internal skeletons, the specific fixtures and supports, the propulsion support structure, external features of the vehicle, and analysis and testing. Under the body tubes, we're focused mostly on obviously the outer structure of the tube and how we are attaching that tube to the skeleton. For the internal skeleton, we're focused on the size of that as well as the configuration of the piece parts and components for the supports. The propulsion structure is highlighted specifically because it has a little bit more of the load distribution to focus on, as well as supporting heavy thermal loads from the combustion chamber and the nozzle. And then here, we're doing lots of different analysis and testing to validate our designs. A lot of it will be simulations, but we hope to be able to do physical testing of static loading, vibrational loading, and thermal testing as well. And for our external features, we have things like the nose cone, the fins, some of those connections of the different sections of the body tube that we're going to have, as well as the parachutes and the recovery system.
I'll be discussing the mission objectives and functional requirements. First, for the mission objectives, the rocket must launch to an altitude of at least 30,000 feet, but no more than 60,000 feet. The rocket will consist of a single-stage engine with a liquid bipropellant pressure-fed engine. Next, the rocket will be successfully recovered after launch. This is a very important objective that we're really emphasizing during this project. Last, there must be a safe operation during assembly and launch. To achieve these objectives, the following functional requirements were developed. First, we must perform functions necessary to precondition the propulsion system and plumbing components prior to ignition. Next, the rocket shall deploy parachutes after reaching apogee. Last, the rocket body shall withstand the dynamic loading conditions during the flight without compromising the successful performance of any other vehicle subsystem. This is a key requirement that has a huge impact on the success of the mission. Next slide. And for the design, these are the main features of the design we've created. First, an internal skeleton structure consisting of bulk plates and threaded rods. Next, bulk plates, fixtures, and supports that keep the structure together and connect to other subsystems and the body tube. Next, a thrust conversion assembly to support the propulsion system. And last, body tube and fins to prepare for flight. These features will be discussed in greater detail later in slides with trade studies and CAD models.
All right, so this is our trade study for deciding the internal skeleton structure. And this structure is what we will use to support the forces that our rocket will experience and to just hold it together. So we started with 3 different proposed designs. We have a skin-based design with all the support built into the skin itself. Then a design where the loads are distributed between trusses and struts that connect the bulk plate. And then we had a threaded rod and plate design. So in our trade study, we determined that our skin-based design was simply not feasible. We just weren't confident in our ability to manufacture a rocket where all of the loads are distributed throughout the skin. So in our comparison between the threaded rod design and the truss and spar, as you can see, they came out to be pretty close to each other. But ultimately, the threaded rod design, the weight that we'll be saving by using that over the truss and spars decided it for that one. We had originally decided to just use a combination of the two because they were so close, but then we decided to reduce our diameter of the rocket because of changes that came up in our design, and the threaded rod design came out on top because of that. Next slide, please. So these are just some renderings from our CAD model of the internal structure design. The rocket, it will be broken up into compartments. Each compartment has a bulk plate on bottom and top. So this is just a view of one particular compartment. The tank that you see in there is just a preliminary model of the tank. There will of course be plumbing and supports for it, but they're simply not represented in this model, and the tank is just for an idea of what the compartment will look like. So the threaded rod, or the rods, will be 1/4 inch aluminum, and they'll be threaded on the top and bottom. They'll be fitted through the bulk plates, and nuts will be put on the top and bottom of the bulk plates to lock the rods on. In this model, we have 4 rods, as that was our preliminary idea, 4 rods between or in each compartment. We're also working with the idea of 8 rods in each compartment instead of 4. The final decision on which number to go with will be based on our analysis of the structure and how strong the rods are and how many we need to support the loads. Yeah.
All right, so this is the trade study we used to determine the interface between each body section of the rocket. Here we considered bulk plates, carbon fiber layup, and couplers. And we heavily weighted like our cost, our manufacturability, and our weight for this trade study. We determined carbon fiber layup wasn't feasible with our manufacturing capability, and ultimately decided that bulk plates were our best option because they were the easiest to manufacture and they're also the cheapest. Next slide. And then here is our trade study for our attachment method between the bulk plates in the body tube of the rocket and the bulk plates and the threaded rods. Here we considered epoxy, nuts and bolts, and welding. We heavily weighted ease of access, ease of assembly, and cost for this trade study. And we ultimately went with nuts and bolts because of its high scores for ease of access and assembly. Next slide.
Yeah, hi. So the rocket is really separated into 2 systems, the skin and the skeleton, and the bulk plate plays a critical role in this system. So the bulk plate, it will allow for for mounting of critical systems, and it will also be the interface that connects the actual skin and the skeleton itself. The bulk plate right now will be made of 3/16 inch aluminum. And if you notice on the CAD models, there are 8 holes on the perimeter. These holes are the mounting holes that the rods will go through, and that is how we will connect 2 bulk plates together. Doing this will allow us to compartmentalize our rocket, which will greatly increase our ease of access and disassembly. The larger holes are like pass-through holes for stuff like fuel lines and electronic lines and everything. And for those, we will be using grommets, NBR grommets that are certified for high vibration environments and also for extreme temperature changes. And I'll hand it off to Danny.
All right, so this is one of the concepts for the connections between the body tube of the rocket and the bulk plates. As you can see in the figure 6, the top half of one body tube section would be epoxied to this L bracket and then bolted to the bulk plate. And then the bottom half of the upper body tube section would be epoxied to this plate off to the far right there. And then that would be bolted into the L bracket on the bulk plate. And then this design shows 8 threaded rods, and they're alternating on the bulk plates. So you have 8 in one section and 8 in the next, so 16 holes in total on each bulk plate. This could be changed. We could use 4, and that will just depend on our analysis. And then here you can see the bottom of that connection method, and it would utilize a welded bolt so that all the holes line up when we go to attach the bolts. And I'll pass it off to Noah for another concept of our connections here.
This is another concept for attaching bulk plates to the body tube. In this design, L brackets are used to connect the bulk plates to the body tube. For each bulk plate, 4 L brackets are permanently attached to the body tube using epoxy. These L brackets have a 0.25-inch nut permanently welded to them, as you can see on the right side of the screen in the pictures. Notches will be cut into the bulk plate so that the internal structure can slide into the body tube without catching on any of the permanent L brackets. After the structure is in the correct position, the bulk plate will then be twisted so that the holes in the bulk plate line up with the holes in the L bracket. And then a 0.25-inch bolt will be placed from the top, which will be open in the body tube and attached to the welded nut, as you can see in the pictures here.
So going off of that to talk about how we're going to support the tanks while these things are also being connected to that. A big key for us is ease of integration and assembly with this. We want to be able to take this apart and put it back together, and we don't want to damage any hardware. So here is a concept of how we are thinking of supporting the tanks while minimizing the material removed from the bulk plates and also properly mitigating the stresses, both thermal and mechanical, that these supports would experience. So this is kind of a cone-shaped cup that would sit on both sides of the tank, as you can see in figure 13. They would be friction mated, so there would be like a gasket material on the inner ring here that would interface directly with the tank, which right now, I'm not sure if it's going to have a composite outer layer or not, but basically we would want a metal to metal seal that could potentially cut into the tanks or somehow cause another failure. So we're obviously going to do analysis on this. It may require bolts or some sort of mechanical attachment to the plates themselves instead of just being a friction mate. But the idea is basically that we could use these and then use the threading and the nuts on here to adjust the positioning of the bulk plates such that everything is held in the proper tension and configuration before we attach the skin.
Okay, now to talk about the thrust conversion assembly. And basically the job of the thrust conversion assembly is to convert the thrust actually and make sure it's going in one direction. So basically it has to sustain the load for the entire burn time, and then it has to survive all the thermal, the high temps and the cryogenic temps, the vibration, all that stuff. And then the key component that I want to do for the thrust conversion assembly is a safety factor of 3. Other key design criteria that we want to have, but we don't need to have, we want it to be simple and easy to manufacture. Obviously, it's got to meet our strength requirements. There is 3 fill lines going through the thrust conversion assembly, so there needs to be enough space between those points that those still fit, and then we can have the design fit through. And then the big point is that your thrust still needs to be going down in one direction. Next slide. So this is the, or at least not the initial concept, this is like the third or fourth design iteration of the thrust conversion assembly. So basically the main point is you have four, I call them thrust struts, and they're 2x1 with a wall thickness of 1/8 inch of rectangular steel tubing. And that's the main thing that's going to be taking the load. And then you have four 1/2 inch threaded rods that are going to be connecting the bulk plates together. And then you have 3 custom U brackets that connect the thrust strut from the combustion chamber to the threaded rods. And then the bolts that connect the thrust strut to the combustion chamber and then connect the thrust strut to the U brackets. Those are 3/8 inch bolts. And another big part is we're going to have proper torque specs for all these bolts, because there's a lot of bolts for everything here, and they need to all be properly torqued. So next slide. I'm going to try to go through this fast because there's a lot of stuff here. So the likely failure modes that I'm kind of freaking out about for this would obviously be a brittle failure of the brackets due to the cryogenic temperatures on the igniter. And then you also have the thermal expansion problem from the bolt that goes from the bottom of the combustion chamber through the igniter that connects the two. So you have cryogenic on one side and thermal on another. So I'm definitely scared about having problems there. And then obviously the bolt shearing. And then also you have the issue if the struts twist and they don't stay perpendicular to each other, you can get a twist of the motor, and then your rocket's going to lean, and then you got big issues. So I just have some ways to minimize it, which is obviously thermal analysis using heat-treated bolts, so you're not having any issues or too much issues with thermal expansion or losing strength between your connection to the igniter and the combustion chamber. And then obviously using the correct bulk sizing, and I'm using NASA System Engineering Handbook for that. And then we're going to have a procedure to make sure that all the thrust struts are basically level. Next slide, please. And this is just a list of materials that I want to use or I'm thinking about using for the struts, bolts, and nuts. I want them all to be 304 stainless, so we don't have any problems with locks and nothing too brittle. Currently, the bulk plates and the brackets, so you have the one bracket that connects to the igniter, and then you have the 2 that are connected via bolts, and then they connect to the threaded rod. Those are going to be aluminum. I'm a bit sketched out that the one is connected to the igniter is aluminum. If the thermal analysis comes back, I'm definitely changing that to 304 stainless or some other material if that doesn't work either. And then the threaded rod is AISI 4140, which is just grade B7. I found both specs, so I don't know which one is right, but that's what it was. Then I'll hand it off to Cody.
Cody, your mic is muted.
Thank you. Sorry. So this is our body tube and our body tube skin trade study. So basically, we were looking for a lightweight, thin-walled structure, obviously, something that can withstand our aerodynamic loads and all that good stuff. So basically, based on everything that we looked at, we chose carbon fiber for most of the structure. We're going to split it up into 5 different sections. The sections are going to range somewhere between 4 to 6 feet in length, depending on what we need for that section. In our avionics bay, however, obviously it's not going to, we're going to have some transmission issues if we use carbon fiber. So for that section specifically, we're going to use fiberglass. Only reason I think right now that we probably wouldn't use fiberglass for the entire length is just because of we're dealing with some weight issues and it's going to be a little bit heavier. But yeah, go ahead, next slide. And this is kind of what we're thinking about the fins for right now. We're still kind of doing trade studies on it. I think a fin can probably is our best option. I've actually been looking at where we're going to get the carbon fiber tubes from, and I found a company that will also make the fins for us as well in-house. They do a lot of unusual projects and things like that for DoD and different rocketry teams. So I think our best bet is to have like a fin can system, and hopefully the manufacturer for that carbon fiber tubing can do it for us. But yeah, that's what I'm looking at right now, and I'll hand it off.
Yeah, so I'm just going to go over some major risks real quick. One of the biggest risks for us is parachute deployment failure. We've been definitely stressing out, making sure that our recovery system works, especially Dr. Brandon has been telling us to do that. So we want to make sure that we will become the first ARES rocket to actually recover. Loss trajectory and loss of stability, those are kind of intertwined. That can just caused by a lot of asymmetric loading or asymmetric mass imbalance or whatever. So there's a lot of things we have to consider, but we have like a series of checks and analysis to make sure that that will not occur. Next slide, please. Connection point failure is really important. This is a system with a lot of connection points. There's a lot of like bolts, nuts, everything like that that could fail. So again, we're doing analysis and specs and everything to make sure that those connection points will not fail. But one of the big supports, connection points actually too, is failure of tank supports, because we need the tanks in order to fly. And there's just a lot of variables that can happen that can cause a failure of a tank support. Since the tanks are cryogenic and everything, they can be incredibly cold. They could break one of the supports, and that could go make the tank off balance, or it could go and slosh around and hit a bunch of different supports. So again, we're doing a lot of analysis to make sure that that will not occur. Thermal loading also, rockets, they get exposed to a wide variety of thermal loads, be it extreme temperatures from the heat, or again, the cryogenic fuel causes it to be super cold. But again, we'll be using stuff like ANSYS and SolidWorks and everything to make sure that all of our rocket materials meet specs. Yeah, next slide. Anyways, here's the projected expenses as well. Again, these are just estimated. But again, this rocket is so large and it contains so much material that it can get pretty expensive pretty quickly, especially with welding. If we use stuff with aluminum, welding aluminum is a little bit difficult. And the bulk plates too, they're just slabs of aluminum. Those get pretty expensive. Same thing with the composite skin. That's going to get pretty expensive just because of how large it is. But again, we have good budget managers to make sure that we will not go over our budget, and we'll try to get donations and discounts whenever we can. Next slide, please.
So these are just kind of our next steps looking ahead for our project, especially as we move into our CDR for our senior design class. As of now, we've pretty much completed our first iteration of the assembly, and so we're moving into various different simulations so we can validate, modify, iterate, do everything that we can to make sure that we have a solid design before we start purchasing thousands of dollars worth material. So that is our key focus going into this, and then assuming that that all works out, we will start building and assembling and testing the structure throughout this spring. And these are just acknowledgements of everyone who has supported us through this project so far and all of the help we've received. But thank you guys so much. And are there any questions you would like addressed at this time?